Welcome back, guys. In this video we are finding extrema again using the first derivative test. So here's the problem statement. So let's say we are asked to find the open intervals where the function is increasing or decreasing, and we are asked to find and classify relative extrema of a given function using the first derivative test, and we're asked to graph the function. In this video, as compared to the other videos, we're doing something a little different. The example function involves a trig function. It has a sign of x in it. So that makes the process for actually finding those intervals a little bit more involved, as I'll show you. So the first thing we do with all of these problems is we find the domain of the function. Because when we're testing and classifying relative extrema, we're really only interested in x values in the domain. All extrema happen at x values in the domain. And having a sense of where that domain starts and stops and what the limits of that domain are, well, that's also going to help us define the intervals where f is increasing or decreasing, because it can only be increasing or decreasing on an interval where it's well defined. So we find the domain first. Notice that x is a continuous function, it's just a linear function. We know sine of x is that continuous sine wave. It keeps going in both directions infinitely, or infinitely to the left, infinitely to the right. We've got the sine function the whole time. So this is well defined and that's well defined, so the difference is well defined. So the domain of f happens to be all real numbers. And that's good, there are no restrictions on f. The next thing we want to do, if we want to find the intervals where f is increasing or decreasing, is we need to figure out where it could possibly transition from being increasing to decreasing. And the function can possibly transition from increasing to decreasing at critical points. So the first thing after finding the domain, the first thing we do is we find the critical points of the function. And remember what critical points are. Those are the x values where the slope of the graph is 0 or where the slope is undefined. Those are potential relative extrema. They also mark the endpoints of the interval where the functions goes from potentially from decreasing to increasing or increasing to decreasing over there, and so on. Here's another critical point, decreasing to increasing. But algebraically, the way we find those points is we compute the first derivative, we set that first derivative equal to 0 and solve for x. Those are giving us the x values where the slope of the graph is 0, and then you need to consider any x values in the domain where this derivative is undefined. So find any x in the domain for which f prime is undefined. Those are critical points too. So let's compute the derivative of this function. Derivative of x is just 1. Bring the 2 down. The derivative of sine of x is cosine of x. Now cosine is well defined for all real numbers, so we can multiply it by 2 and add 1, and it's still well defined for all real numbers. So we don't have to worry about anything that's described right here. But we should set f prime equal to 0 and solve for x. Now, it's probably been a little while since trig, but now we're just solving a simple trigonometric equation. Now because of the fact that these trig functions, sine and cosine, well, all 6 trig functions are periodic, this equation has infinitely many solutions. Let's solve it for cosine of x first. I'll subtract 1 from both sides, divide both sides by -2, and I get cosine of x equals 1/2. Now cosine looks like this, and it repeats for all time. When I'm trying to solve this equation, what I'm looking for are the x values where y equals 1/2 crosses that graph. Well, y equals 1/2 crosses the graph of y equals cosine of x infinitely many times, there and there and there and there and there and there, and just forever. So what we usually do when we want to solve a trigonometric equation for all x values is first we find the solutions on the interval from 0 to 2 pi. So we find the solutions over one period. And then we add multiples of 2 pi to get all of the other solutions. Because this solution right here and that solution right there are related to each other. I just take that solution and I add 2 pi to get the next one. And I take that solution and I add 2 pi to get the next one. That one. And if I take this and add 2 pi, I'm going to get another one that's over here. And if I take this and add 2 pi, I'll get another one over there. And so on. So really, if we could just find those first two solutions, those solutions on the interval from 0 to 2 pi, we'd be good to go. Okay, so in order to do that, rather than trying to look at this graph and infer, because it's just sort of a cartoon graph, it doesn't have all the details, it's not very clear what the x values are that are associated with y equals 1/2, I'm going to draw triangles in the xy plane. Now remember, cosine is positive whenever x is positive. And I'm not talking about that x. That's going to be our angle. But cosine of theta is positive, a positive 1/2 whenever x is positive. So I'll draw two triangles, one in quadrant 1 where x is positive and one in quadrant 4 where x is positive. Now cosine from SOHCAHTOA, remember that mnemonic? We remember cosine is adjacent over hypotenuse. So what this tells us is we're looking for the angle where the adjacent side of the triangle is 1 when the hypotenuse is 2. Well, those are two sides of a 1, 2 square root of 3 triangle. That side has to have length square root of 3. That side has length square root of 3. But since the y is negative here, we put a -1 out front. The angle x is that angle there and that angle there. So the first one, well, that's opposite the square root of 3 in a 1, 2 square root of 3 triangle. We remember from trig that's a 60-degree angle. 60 degrees is 1/3 of 180. So that's 1/3 of pi, or pi over 3 radians. And this is -60 degrees. But if I want the angles between 0 and 2 pi, so that I can add 2 pi to all of them, instead of thinking of this as -60 degrees, I'm going to think of it as 360 minus 60. So that angle is 300 degrees, which is pi. That's 3 pi over 3 plus 2 pi over 3. So we get 5 pi over 3. It's 5/3 of pi. Okay, so those are our first two answers. But the critical points, those are all of the x values that satisfy this. They come from taking these two answers and then adding multiples of 2 pi or subtracting multiples of 2 pi as many times as we want. So the critical points of our function are the x values for which f prime is equal to 0. F prime is equal to 0 when x equals pi over 3 plus any multiple of 2 pi I want. So it's 2 pi times n, where n is an integer. Or x is equal to 5 pi over 3 plus or minus 2 pi n, as many times 2 pi as many times as I want. And adding that 2 pi n to each of those is effectively adding and subtracting 2 pi as many times as we want to get all of those angles. So we found our critical points. Now that we've got the critical points, we want to find the open intervals where f is increasing or decreasing. And in order to do that, I need to find the sign of f prime on the intervals defined by these critical points. And there are infinitely many intervals. So let's do that on another page. f prime is 1 minus 2 cosine of x, and we know that f prime is equal to 0 when x equals pi over 3 plus 2 pi n, where n is an integer, and when x equals 5 pi over 3 plus 2 pi n, where n is an integer. So if I draw these on a number line, I'll draw pi over 3 here and 5 pi over 3 here. I know that this is not to scale. And then I'm just going to focus on that one, and I'll add 2 pi. And 2 pi is the same as 6 pi over 3, because 6 divided by 3 is 2. So I'm adding 6 pi over 3 to this, so I get 7 pi over 3. And if I add 6 pi over 3 to that, I'll get 13 pi over 3. Now I can also subtract 6 pi over 6, or 6 pi over 3 from this. So that would land me over here at negative 5 pi over 3. Or I can subtract 6 pi over 3 from that, and I'll get negative 11 pi over 3. Okay, and then we're going to do the same thing with the 5 pi over 3. Add 6 pi over 3, and we get 11 pi over 3. Subtract 6 pi over 3 from this, and we get negative pi over 3. Subtract 6 pi over 3 from that, and we get negative 7 pi over 3. And so on. This pattern continues forever. All the red numbers come from these guys, and all of the black numbers, except for the one I circled in red, those come from the second one. Okay, so we just want to know, what is the SIGN sign of this on these intervals? Well, one way that we can find it is to graph this function 1 minus 2 cosine of x, and then just look at where the y values on that graph, the graph of f prime, are positive and negative. So in order to do that, first we'll start with the cosine graph. And I'm just going to graph it for 0 to 2 pi at first. We know cosine starts at its max. So it goes max, 0, min, 0, max. So that's what y equals cosine of x looks like. Now, if I multiply by negative 2, it's going to look almost exactly the same. But multiplying by a negative flips it. So instead of starting at the top, we start at the bottom. And instead of going from negative 1 to 1, I'm going to go from negative 2 to 2. I'll just label my tick marks differently. So it goes min, 0, max, 0, min, and that center line is on the x-axis right now. Oops. It's not a very pretty cosine curve, that's okay. But it continues. There should be arrows on these guys. Continues forever in both directions. Okay. Now we're going to take this graph and we're going to add 1 to it. So it's going to shift the whole thing up 1 unit. It's also going to change our center line. Our center line right now is on the x-axis. When I shift up 1 unit, I'm going to draw the whole thing now so that I can fill in that number line over there. My center line is going to shift up to y equals 1. So instead of going from negative 2 to 2, if I add 1 to everything, I'm going from negative 1 to 3. So we're going to start at the bottom, negative 1. Then at pi over 2, we're on the center line. Then at pi, we're at the max. Then we're back on the center line. Then we're at the min. And so it looks like this. And it repeats. Now, if you're saying to yourself, how is that going to help me? Well, remember, f prime is 0 at pi over 3 and 5 pi over 3. So even though it looks bad, that's actually pi over 3, and this is not to scale, obviously. That's 5 pi over 3. And the pattern continues. So it's going to look like this. I think we can see what's going to happen. Well, f prime is negative anytime that curve is below the x-axis. The curve is below the x-axis on this first interval from negative pi over 3 to pi over 3, so it's negative there. Then between pi over 3 and 5 pi over 3, the y values are positive on the derivative graph. So that's positive. Then from here to here, they're negative, then positive. And we see that the pattern is alternating, it repeats. Indefinitely. Okay, so the question said, I find the open intervals where f is increasing and decreasing. Oh dear, how do we explain, how do we describe all of these guys at the same time? Well, it looks like trying to identify the ones where f is increasing. So it's increasing there, increasing there, increasing there, increasing there, increasing there. So I think I'm just going to focus on this first one, that one between pi over 3 and 5 pi over 3. And then I'll say, you know what? You can add 2 pi to that, and you end up here. Add 2 pi to that, and you end up here. And it's going to be positive over there as well. And if we add 2 pi to both of these guys, we're going to be on that next interval. So f is increasing. On the interval from pi over 3 plus 2 pi n to 5 pi over 3 plus 2 pi n, where n is an integer. And we could say that f is decreasing over here and decreasing over here on 2 separate intervals, but I think this is a special case of this one as well. So let's focus on this one. F is decreasing where the derivative is negative. F is decreasing on the interval from 5 pi over 3 to 7 pi over 3. But in order to get the next interval, I can add 2 pi n to this, and add 2 pi n to this. And again, n is an integer. Oops, sorry, that's off the screen. Okay, so we've answered the first question. It asks us to find the intervals where f is increasing or decreasing. Now we want to classify the relative extrema using the first derivative test. Well, I can see just from this number line where I have extrema. So I've got negative pi over 3, pi over 3, 5 pi over 3, and then 7 pi over 3. And the pattern repeats. And that was negative, positive, negative, and there's a positive and a positive over there. So this is f prime. These are the signs of f prime. If f prime is positive, that means the function, the original function f, is increasing. So the function is increasing on each of these intervals. If f prime is negative, that means the original function f is decreasing. We just found those intervals where it was increasing and decreasing. Well, what does that mean for these points? Well, it means if it goes from increasing to having a 0 slope to decreasing, I'll have a max there at pi over 3, or negative pi over 3. If it goes from decreasing to having a 0 slope to increasing, I'll have a min. So it's increasing, 0 slope, decreasing, max, decreasing, 0 slope, increasing, min. And this pattern repeats. So we're going to have a max and a min and a max and a min, and it's going to repeat indefinitely. You're like, okay, well, how do we describe them all again? Well, it looks like the minima occur at pi over 3 and 7 pi over 3, and then the next one when you add 2 pi to that, and so on. So we'll say f has relative minima at x equals pi over 3 plus 2 pi n, where n is an integer. If you're saying to yourself, well, what is the value of f at those minima? Well, f of x was x minus 2 sine of x. So when I evaluate this at pi over 3 plus 2 pi n, this is what we get. So I'm replacing x with pi over 3 plus 2 pi n. Now, adding and subtracting 2 pi inside a sine function doesn't do anything. So this is the same as this, because sine repeats. It's periodic. Every 2 pi, I get the same thing. So I don't really need this 2 pi n. So I got minus 2 times sine of pi over 3, which is 60 degrees. And we know sine is from SOHCAHTOA, opposite over hypotenuse. This is square root of 3 over 2. So we get pi over 3 plus 2 pi n minus square root of 3. And I think I want to just estimate what that is numerically. Pi divided by 3 minus square root of 3, that's giving us this constant, negative 0.685 approximately. Then we're adding 2 pi, which I think we all know what that approximation is already, 6.28 times n. So every n, the function value is increasing by 6.28. Okay, and those are all relative mins. At these x values, we get these y values. We're going to use that to graph the function in a little bit. Okay, so those are our relative mins. It's a lot of writing just to state the relative minima. And then the maxima occur over here at 5 pi over 3. And if I subtract pi or 2 pi from that, I get negative pi over 3. Or if I add 2 pi to that, I get 11 pi over 3. So we get relative maxima at the 5 pi over 3s. So 5 pi over 3 plus multiples of 2 pi. And the maximum value at each of those x values is given by this. The f of x is x minus 2 times sine of x. I'm replacing x with 5 pi over 3 plus 2 pi n. And again, sine repeats every 2 pi, so I don't really need that. I'm going to get the same value every time. I'm going to get sine of 5 pi over 3, which is the same as sine of negative 60 degrees. It's a 1, 2 square root of 3 triangle. So we'll have negative square root of 3 over 2. The negative times the negative is a positive. The 2's reduce. and we get 5 pi over 3 plus 2 pi n plus square root of 3. And that's approximately equal to this. And I normally don't do a numerical approximation, but in order to get a better sense of what's going on here, I think it makes sense in this case. So there's my 5 pi over 3. I'm adding square root of 3, and I want a numerical approximation. So I get 6.97 approximately, and then this is going to be 6.28 times n. Okay, so those are our relative maxima. And now we want to graph the function. Well, we know that f of pi over 3 plus 2 pi n is approximately negative 0.685 plus 6.28 n. And f of 5 pi over 3 plus 2 pi n is approximately that, 6.97 plus 6.28 times n. So what does that mean? Well, let's look at the first couple of values. When n equals 0, what do we get? And I guess we need a numerical approximation of pi over 3. I think we can all probably do that one in our heads as well, but let's say we don't want to. Then we get that. Multiply that by 5 to get an approximation of 5 pi over 3. Okay, so when n is 0, this is saying when x is 1.05 approximately. The y value on this graph is, when n is 0, negative 0.685. And that was a relative min. And then at 5 pi over 3, so that's 5.24. So this is 1, 2, 3, 4, 5. It's going to be a little bit more than that. The y value is almost 7. This is not going to look good, not to scale. I say, okay, but what's happening? Yeah, my graph is not so great. We get a minimum over here, and then over here near 5 we get a maximum. Okay, well, what's happening? Well, every time to get another minimum, I'm going to add 6.28 to the x value. So I'm going to go over here. And then I'm also going to add 6.28 to the y values. So what we'll see, we're going to see something that looks like this. Does that make sense? I'm taking these two original points. If I add 6.28 to the x and I add 6.28 to the y, it ends up here. If I add 6.28 to the x again and add 6.28 to the y again, it gets right there. Then there, and there, and there, and it continues. And the same thing is happening with this. I add 6.28 to the x, and then I add 6.28 to the y. So that initial min becomes this family of mins. And of course my graph is not to scale. I was trying to draw it to scale over here, but it was going to take a really long time. And that precision wasn't really going to help us. It was more the idea that we were interested in. And the same thing is true here. We're going to add 6.28 to the x and add 6.28 to the y. Over and over and over again. And it gets us all the relative maxes and all the relative mins. So that is my very, very rough sketch of this function.